Good morning, good afternoon, good evening to everyone joining us from around the world. My name is David Sawyer. It's my great pleasure to welcome everyone on Zoom, everyone on YouTube, and everyone on LinkedIn to today's tinyML talk. Today we're going to talk about unleashing the power of tiny neural network models in medical devices from Jim Huang and Steve Yu at University of Sydney. It is now 8 a.m. Pacific, so let's go. First of all, as always, we'd like to thank our sponsors who make tinyML possible. AIZip, Arduino, ARM, BrainChip, Edge Impulse, Embed UR, Befficient, Greenwaves Technologies, Gravity Inc., Timax, Imagimo, Infineon, Initera, Noda AI, NXP, Procter & Gamble, Qorvo, Qualcomm, Renesas, Schneider Electric, SensiML, Sony, Silicon Labs, STMicro, Synaptics, Sentient, and TDK. Thank you for making tinyML possible. If you are familiar with tinyML, if you're new to it, both of these are great places to get involved. We have a growing meetup group with over 20,000 members in 42 countries. And the tinyML community on LinkedIn is available here at the URL or QR code with over 4,000 members and 16,000 very active followers. In addition to the meetup groups and LinkedIn, we have a couple of ways you guys can get involved. Also, the YouTube channel. So the YouTube channel is where all the material from tinyML is available for free all the time. All the talks like this one will be posted there, so you can subscribe and stay notified from all the stuff happening all across the world in tinyML. And coming up, this is a super exciting in-person event. We do have a few in-person events that happen around the year, around the globe. tinyML EMEA is in Milan, Italy, June 24th to 26th. So be sure to register now. This is one of the most fantastic ways to get involved by actually going to one of these live events. So I have a great pleasure to welcome our first of two speakers. Jim Huang is a second-year PhD student in the School of Biomedical Engineering at the University of Sydney. His research focuses on the application of tinyML and the analysis of biosignal data, particularly in the realm of medical diagnostics. With a keen interest in leveraging cutting-edge technology for healthcare advancements, he is committed to exploring the potential of machine learning in addressing critical challenges in biomedical engineering. And Jim will be joined by his colleague Steve Yu. Steve is a second-year master's student at the University of Sydney School of Biomedical Engineering. He's dedicated to researching circuit design, signal processing, and system development, particularly in the realm of biosignal hardware, showcasing a strong interest in exploring diverse devices for biosignal measurements. Steve, Jim, thanks very much for being here. Looking forward to your talk. Please take it away.
All right. Thank you, David, for introduction. My name is Jim, and I'm here with my colleague Steve, and we are going to talk about how we can apply tiny neural networks in wearable devices. And we currently are based in Sydney, and it's late evening here, so if we act a bit slow and please be patient. Thank you. And first of all, I'll just pass on to my colleague, Steve, and he'll be talking about some backgrounds and some challenges that we'll be facing in the research fields. And then I will be carry on from there to talk about the current progress that we have and the future directions of our research. And we will welcome questions along the way. So if you have any questions, please drop in the Q&A chat box, and then we'll be happy to take the questions along the way. So now I'll hand over to my colleague Steve to start with the presentation of the day. Thank you.
Okay, thank you, Jim. So the presentation is divided into 5 different sections. For the first 2 sections, we will be talking about the background and the current challenges of the field. Well, for the later sections, we are going to talk about the context regarding to our research. Then we start with the introduction part. Our research is currently focusing on the biosignal devices. Well, among all different device wearables, these days are becoming a more and more popular type of device for recording biosignals. Wearables are the device that you can wear every day. Various wearable devices with diverse applications are available to gather various physiological data. These devices also process the captured signals using techniques showing on the screen. In the healthcare domain, this device are utilized for various applications. For example, the current device shown on the slide is a device for recording EEG signals. It can have several different applications like brain-computer interface, so that you can control your light in your home with the thoughts of your brain, or it can also used for like the recording the seizure recording for seizure detection. Apart from the medical device, there has been a large improvement in the machine learning. Machine learning has been applied in many fields. It is also happening in the fields that we are currently working on. Specifically in the medical field, machine learning can help health professionals to identify parameter patterns within data that have been related to some specific disease. This not only helps them to save their time and the decision-making time, but also allows doctor to focus on their time on the more important things like how to cure the disease. By automatically marks a certain time part of the data, machine learning also simplify the patient care and treatment procedures, and this leads to a more efficient and effective healthcare delivery. Moreover, machine learning helps in the early identification of the potential issue from the biosignals, enabling early treatment. This approach contributes to better patient outcomes and overall healthcare management. The integrating of machine learning into healthcare not only enhances the diagnosis accuracy, but also helps to develop more personalized patient management strategies. Therefore, achieving precise AI processing on resource-limited device becomes more necessary now. With that in mind, our goals here are to optimize biosignal models so that they can operate with low latency and minimal power consumption while meeting the performance of the AI model. Then we are going to talk about several current challenges we are meeting in the research field. Currently, there are several different challenges in the field, and we are going to focus on the 5 we think the most critical ones. Model generalizability, which is the ability for the model to operate on external datasets. After training on the existing dataset, the model will need to operate on a totally different patient out of the dataset, and it's still required to have a very good performance. Personalization is the ability to customizing algorithms for specific user preference to offer like a better accuracy. Like it is usually done by training the model with the user's own data. Model size basically is the size of the model and the memory needed for the model to operating. This is important because we are operating our model on the edge device, and on edge device there is very limited computation resource, so we need to be careful with the model size. Model performance. Basically, this is the accuracy, latency, and the resource efficiency of the model, and we need to have a very good performance so that it can really do its job. Power consumption is basically the power needed for the model to operating on the device. This is important because for the wearables, they are basically rely on the batteries to operating. Generalizability is one of the major challenges of the model. There are 3 different aspects of the things like it will influence the generalizability of the model. For example, different group of people will have like different features regarding to the signal, and this will lead to the difference in the biosignals. Therefore, we need to be careful with that. And regarding to the environmental factors, for example, noise. For different regions in the world, for example, the pollen noise, it can be 50 Hz or 60 Hz. Also, when you are walking around with around a machine which is operating, it will also lead to a noise with a certain frequency in the signal. Therefore, the model needs to be able to handle all these different conditions of the noise, and also motion artifacts. While we're using our model on the wearables, this means like the patient will not sit there and do the recording. The patient may walking around, running around, or even jumping up and down. And this means like this will cause a huge amount of motion artifacts. And the model needs to be able to handle all these motion artifacts. And also, so the long-term adaptability. The patient is not, they will change their daily behavior. If they start to drinking coffee in the morning, and this will also lead to the changing of the bell signals of the patient. Therefore, the model needs to be able to handle all these different conditions. Regarding to the personalization, the major solution for the personalization is fine-tuning. Fine-tuning of the model is based on basically use the user's own data to train the model, to fine-tune the model. However, this method is kind of limited on the aged device. This is because like on the aged device, the memory is constrained. Therefore the complexity and the size of the model is very limited. For current topic here, which involves running a model on one aged device, model size is also critical to consider. For most of the aged device, they have very limited memory, and if a large model will lead to the memory to overflow and operational crash, and this will basically lead to the whole failure of the system. Therefore, it is necessary to create a compact, efficient models and to find a balance between the model size and accuracy. Model performance is the critical challenge of the machine learning. So this is important because like model performance is basically the major reason why we're using this model. It needs to be very accurate. It needs to be very accurate. Otherwise, the result it outcomes will not be trustworthy and not reliable, and then it will be meaningless. Regarding to the latency is something also very important for a wearable device. Because like it can produce a low latency can produce a very low response time. This means like in the applications like seizure detection, patient may hurt themselves when the seizure occurred. So they need to have an instant response when the device detects a seizure. But if the latency is too long, then there's no meaning for them to like detect a seizure and to prevent them from being damaged by themselves. And also like the resources need to be considered well, because like still we are operating on an aged device, and this means the memory, the power consumption of the device is limited, and therefore we need to like try to still find the balance between the performance and the resource. Regarding to the power consumption of the model, some device here we used, they are not only operating for like several hours, they may need to be operating for like days, weeks, or even years. And in order to extend the battery life or like reduce the frequency of recharging, we need to design the model which is like crucial to achieve the optimal battery efficiency. This includes like developing an energy efficiency model for data processing, interference, and communication to minimize the computation load and the power usage. Additionally, choosing like the low power consumption components in the hardware domain is essential to reduce power while ensuring optimal performance levels, like the different chips or different pre-processing components, like the different op-amps. Then we pass the presentation to my co-worker, Jim.
Oh yeah, okay. Just wondering up to this point if there's any questions. I'm happy to take?
Yeah. So there's a couple of questions here. Jim or Steve, whoever wants to answer it. First question is from Fareed. What type of biosensors besides ECG and EKG applications are being used considered for tinyML medical monitoring? Use cases and who makes these use cases? That's the first question.
Okay. So I think for what the research we are currently doing, we are actually using ECG and EEG most of the time. I'm aware that there has been other kind of biosignals that have been tested on. For instance, the PPGs, and I think there's like muscle movements as well even. So there has been some growing applications of biosignals in this kind of areas.
Cool. And there's a follow-up to that. Who makes these use cases? Is it of the manufacturers, like I guess medical device manufacturers and the models? And there's a subsequent question to that, which is there a database for these sensors? So I think they're wondering, who's providing the relevant, materials for machine learning for these use cases.
Mm-hmm. So for some of the applications, for instance, the EEG and ECG applications that we deal with on daily basis, there are some public data sets for certain applications. For instance, for ECG data sets, there's abnormality data sets, which are public, so you can actually use them to train a model. And I think for EEG, there's seizure data sets that's publicly online. And apart from that, we also work with hospitals and on using some of the private data sets to actually to check if the model that we have built is actually useful in real cases.
Right. Nice. So that's super helpful. And this is also, it's kind of in the same vein. This is a different question from Mahdi Saleh. The question is there specific international standards for certifying the use of ML algorithms on medical devices?
In terms of standards, I'm not quite sure what kind of standard it's referring to, but I mean, if you're talking about ethics, I think there's certain international standards
for FDA or the guidance we have at a national level. So I think the question says international, which maybe there's not as much there, but I mean, in some cases, maybe EMA. I know the FDA has made some progress in how they want to certify software and ML devices, and you'd find guidance there perhaps, but not from the ML community as far as I know. If there's anything that's come from machine learning standards.
Mm-hmm. Yeah, me too, I think.
Yeah. Okay, well, it's also something that a professor involved in the field, Vijay Reddy, is very excited and adamant about. That might be interesting, that question. We'll keep it moving. There is also more question that you might want to address. It's how do you convert deep learning models into C++ code in order to be implemented on the edge devices? So do you use ONNX or XXT tool to convert TF-Lite to C? And then what type of models have you tried this for? So the question is about converting. How do you deploy these models on the edge devices?
Mm-hmm. So we have tried converting, which I will be going through later. We have been trying to convert some of the models to be implemented on microcontrollers, which requires to be in C++ formats. I think for TensorFlow they have actually like a package which you can use to actually transfer or transform some of the models that you have trained to the format that is compatible to microcontrollers. And I think I will be going through some other details regarding because for microcontrollers it's actually just for inference, usually just for inference.
Right.
And for medical applications, we have talked about, there's one challenge that we have talked about is called personalization, which means you have to actually fine tune the model to actually better fit the patient's needs. That we have, for that purposes, we have tried it, not converting that, but using like a slightly more powerful edge devices that is actually powerful enough to actually fine tune a small model with reasonable time on that. So, but okay. I will be going through that in the later part of the presentation.
Okay, let's say that then. There's one thing I wanted to clarify because maybe I misunderstood the question earlier that was about is there a database for these sensors? I mistook that as was there a data set around these sensors? The question is there a database on these devices? So some of the devices you were talking about earlier, from the question on the ECG, EKG, EKG, is there a database of devices?
Database of devices. I don't think there's a specific data set for devices. But I know there has been some manufacturers or industrial players that have been making or manufacturing certain devices for certain applications. But I don't. To my understanding, I haven't found any data sets for devices.
Okay, cool. Well, thank you everyone for all these questions will be dropped in the chat. I don't, Jim, if you want to keep moving, because I think some of the stuff will be addressed in your discussion, and we can jump back in as you like.
Yeah, I think I'll be going forward with the presentation. But if you have any questions, just drop in the chat box, and I'll happy to take it along the way.
Perfect.
So I think I just taking on from my colleague has just presented. So I think we have presented, we have talked about the challenges that we have faced in the research field. So the strategies that we have used to actually going forward is to actually try to for my personal research, I have used ECG data as the primary data set that we use to actually test certain models and also the compatibility of the models for potential on-device purposes applications, and and we have also used to done certain research and studies to actually try to improve the generalizability of the models, and in order to achieve some of the goals that we have or the challenges that we have faced, we have moved away from using really deep neural networks to actually shallower networks, so that it has less parameters, so the model size is smaller, and it might be it can be more it requires less computational resources, and it's more applicable on devices. And also we have studied certain applications where the model can actually use less energy to run on devices. And we have done all this to actually to in our research, this is kind of like the strategies and the goals that we're trying to achieve to from our research. And I think I'll be going through some of the researches we have done so far to actually give the audiences idea that we have what we are trying to achieve. So so we have done a very small but interesting study on improving the generalizability of the models. So I think my colleague Steve has mentioned about the the idea of generalizability is sometimes when you train the model on a data set, and then when you test it the model on another data set, which is not within the same data set, and you always see quite a big drop in performance. And this is some of the areas that has been caught our attention. So what we have done is the idea is how can we actually improve the generalizability of the model with the same data set with minimum efforts, and we would like to see if there's any improvements on the generalizability of the model. So for that purpose, we have taken this model, and this is the model that has been published in one of the papers in 2020. I think it claims that it has been trained on the world's largest 12-lead ECG dataset, and also the model is fairly large compared to the model that we have used in the later part of the research. But we have used this data to this model to actually test the generalizability. If we can improve that. So how we did it is quite simple actually. The idea is we focused on the characteristics of the data sets. So we actually, instead of just using the whole data set, this whole data set actually comprises of about 2 million individual data, and we actually made a subset from this large data set, and with different criteria. So you can actually see here that how we actually selected the data. So basically, there are a number of abnormalities in the data, and one way we have tried to do it is try to get a very balanced data set. So you can see that for every abnormalities here, it's all for example, the first data sets it's much more balanced compared to the rest, and we have also tried to actually select the data based on other criteria. Say, I think the second data set we tested was trying to pick on patients who has more than one abnormality in their ECG. And the third one, for example, we actually focused on older and younger patients instead of just basically randomly picking the patients. So from the test, I think this next slide I actually have. So I think from the test we have done, we actually have observed something very interesting that we actually with the data set we have selected, compared to the large data sets, this data set is only 1% of the large data set. But in performance, I'm talking about generalization performance, not just in sample performance. The model actually performs slightly better than the model that has been trained on on 2 million data sets. So it's quite surprising that not when focusing on the balance of the data or characteristic of the data, we can actually improve the the performance of the model in generalization. So I think that's the first kind of small work that we have done to address some of the challenges that we have talked about earlier. And before I move on to the next work, if there's any question, I'm happy to take regarding this.
Yes. So just pulling them up here, there are two questions we have. The first one, I think it relates to something Steve presented as well. It says, you mentioned something along the lines of reducing latency for timely disease detection. Could you elaborate on that further?
Time disease detection. Oh, okay. So for instance, I think what Steve was referring to is, for instance, that for seizure detections, we need to process the EEG data on device on the spot, and you will give the detection to the patient that says, "Oh, your seizure is hitting you, and you have to take the medicine or the precautions." So the latency is how long does the model take to actually figure it out.
Right.
So it's quite important in addressing certain illness. For example, that the seizure I have talked about is one of them.
Nice. That's very cool. That's definitely a clear benefit. The other question is, I am just curious to know the amount of RAM and ROM size used by the project that you are currently flashing on your medical devices.
Okay. I think I'm going to present a few of the works. So I think on one of them, for inferences, we actually run it on a STM32 microcontroller, and I think the RAM I think we used is about 74%, if I'm not wrong. I have it in slides in the later slides, but yeah, I think that's the number on my head.
Nice. Okay, and one more question here is asking you to elaborate on the rules and tools that you use to reduce the size of the training data set to make it more vital.
The rules and tools. So for this work, we actually the rules and tools we use is basically on data selection. So for instance, I have elaborated that for one data set that we have created, is just to, trying to get equal amount of every abnormality in the data set. And for instance, for another data set we have used, we try to select the people, the patients with older age or younger age, instead of just focusing on the middle ages. So these are the selection criteria. And with these selection criteria, we have actually created a number of data set, and we have trained them, and we have compared them, and we have drawn a conclusion from there.
Awesome. That's really interesting. One more quick question, Jim, for you. It's actually from YouTube. The question is, which controller, I think, meaning microcontroller, you are using?
For the work that we have done is STM32 microcontroller.
I think you mentioned that.
For that,
okay.
Yeah.
ST32, got it. Thank you. Okay, that's all the questions for right now.
Okay, so I'll move on to the next part. Okay, so here is some tests that we have done for certain models that we have used. For this particular work, we did not test it on any hardware devices, because we were just trying to figure out if this is the right model that we should be using for some of the occasions that or some of the applications that we are trying to address. So for this model is the diagonal state space sequence model, and I think if you are following the machine learning community closely, you probably have heard about the Mamba model, which has been released early this year. So this is from the same kind of work. I think this is more like a simpler version of Mamba, and it shares the same foundation with that model. So they claim that this model is very efficient in terms of parameters and computation, and it also has some certain advantages in terms of model size. So for this particular work, we actually have tested this on ECG data, and also this model works well with time sequence data, which is the form which ECG data is in the form of that. So we have actually tested this model, and we actually used compared using multiple layers of the S4D layers to actually see if this model is working. So drawing from the work that we have done on this model, we actually found something quite interesting regarding this model. So I think my colleague Steve has actually talked about noise. The noise can be quite destructive in biosignals, and this model has shown some resistance to the environmental noises. So it's quite a interesting phenomenon that we have observed from this model, and also the generalizability of the model is quite strong. So we have actually in this work, because we have the conclusion that we have drawn from the previous work that training on a more balanced data set actually improves the generalization capability of the model. So we actually used a very balanced data set to actually train the model and tested it on another data set, which is not the same one that we have trained it on. And we have seen, relatively quite strong holding up of the performance when you tested on another data set. And also another very interesting, phenomenon that we have observed from this model is that usually we use 12-lead ECGs to make predictions or detections of the abnormalities that happening in your heart. For this model, we actually just used 1 channels instead of the 12 channels provided, and we actually have tried to see if this model is still holding up. And very surprisingly, the performance didn't drop by too much, so it's actually holding up quite strong with the with just 1 liter of data. So we are saving 11 liters of data, and this will save a lot of resources on computation. And that's why we think this could be a good candidate for wearable devices. Okay, I think that's the summary of this work. So if you have any question regarding this before I move on to the next one, you're happy to drop in the chat box.
So yeah, the first one, I think this is a great question actually. Do you think this model code be made available?
We have published this work, and the code access has been put on the work. So I think you can access that through GitHub. That the link will be provided on the page.
Yeah, perfect. Yeah, that's what I was going to say. If you have a link or something, you can actually even type it in the answer, and that way everyone can see it. And you could share.
I just realized actually I can see that questions.
Yeah, absolutely. So I think that those could definitely be shared. This is another good question. Under what scenarios do the models on the device need to be updated?
I don't quite get what the. So what do you mean updates?
Maybe update the weights, like do some fine tuning or retrain the model essentially, I think, or maybe change the model more deeply.
Okay, so for some instances, like we have talked about personalization, and this is actually linked to generalization as well. So when you train a model on a public data set or on a large data set, there might be a chance that when this model is applied on this person, and it does not work as what it should be, because of certain features you have, or certain the environment might be different. So in that cases, you might need to fine tune the model with your own data to actually make the predictions more accurate. If that answers the question, yeah.
Right, and even once you've done that, like say you've taken a model and you've used your own data, your own annotations to now train it, and you've deployed it to the devices. Maybe after a month or 2 months, you notice that the accuracy starts to degrade, or you have a new type of drift in the inputs.
Yeah, that could happen. Yeah, that could happen. Yeah. So for instance, the user habit changes, and that could result in the change in your signal. And also, of course, you might need to fine tune that model as well in that cases.
Right.
Okay. Next one. Do you have a...
Yeah. So there's another question. There's one more question that's probably going to be addressed if you share the link or the code. But the question is, do you have some precise figures to share when you're talking about the performance of your model?
I don't have it on the slides, but I'm pretty sure it's there in the paper, in the published paper. So maybe, Steve, can you help me to actually put the link of the paper there? So yeah, you can actually check over there.
Awesome. Well, thanks, guys. Yeah, that's super helpful. I think that's a really interesting part of what's been new in what you presented here is the model contribution. So definitely a lot of interest in that.
Okay, that's good. So I think that's all the questions for now.
Yeah.
So maybe I'll just move on to the next part. Oh, okay. So this is another work that we have done so far. So we have tested another interesting model. It's called neural circuit policy, and this is a very interesting network that they have presented that it's bio-inspired, and they claim that these neurons are much more efficient than the MLPs that we use in our daily machine algorithms. So this model, they in the paper where they published this the work, they claim that they're actually able to drive a car with just 19 neurons. And we were interested to know if this this network can actually be applied to biosignals, where we will be able to use less neurons, which means less parameters, and to make the accurate predictions. So we actually tested this, and with a very, very simple model. So we, as you can see, we process the raw ECG data with short-term Fourier transformation, which is a typical thing that in biosignal area that you use to actually transform this the data from time domain to frequency domain. So and then we used a very just one layer of COM LSTM layer to actually trying to extract the features from the SFT ECG data, and then we actually put those features into a very simple neural network. I think it was I think there was just 20 neurons in there, 20 NCP neurons in there, and we were able to get quite an accurate predictions for the results. So as I mentioned, we have actually deployed this model on our STM32 microcontroller to actually see if this model is actually compatible for on-device inferences. So we actually, and as I mentioned, we always test for generalization of the model. So we have actually trained this model on one data set and tested on another data set. So, and there are two ways you can actually group the NCP neurons, and that's the two models that we have tried. It's called CLTC and CCFC. And then we have also compared these two models, and they behave very similar, but also slightly different. But we found that the CFC model is actually slightly quicker or slightly faster than the other model. So it's actually it's actually better to for if you want to reduce the latency to actually get quicker predictions from the model. And so I think that's kind of the summary that about this work, and this work is also published, and I think the code is in the paper as well. So if you're interested, you can have a look. And if you have any question regarding this work, yeah, feel free to drop it now.
Yeah, Jim, thanks for both those links. I think Steve also shared one with everyone in the chat as well for the previous paper. There's one question related to what you just presented. Do you think that this model could generalize well to other types of biosensors, i.e. biomarkers?
This is a good question, because I've never thought about this, but I think these neurons can be very useful in many areas, because we have tested on multiple type of biosignals, and I have tested on EEG, and we also have tested on EEG, and the performance has been always holding up. So my feeling about this is it could be useful for other biomarkers, but I haven't tested it, so I don't have the definite answer for that.
That's exciting. Is this something that you think people could replicate themselves if they had interest to try your model out essentially on their own sensors or biomarkers and try to see if they can answer that question?
Yes.
That'd be So I think that was your colleagues actually asking the next question. So I think
I think Steve will be putting that on in the chat. So yeah.
Awesome. Okay. Very cool.
Okay, so I should move on to the next one. Okay, so this is another area that we have tried on. So I think in the past, in the earlier part of the presentation, my colleague Steve has talked about the power consumptions of the models. So in certain cases, as he mentioned, we require the devices to be lasting a lot longer than just a few couple of hours. So there's an interesting neural network called spiking neural network, and I think it's also called neuromorphic in certain areas. So what the claim about this kind of neural network is that it's very power efficient, because it works differently from the traditional neural networks. It works on event-based processing, so it detects the changes rather than the whole image. In that example, if you understand, so the power consumption of this kind of neural network is a lot lower because you only focus on the changes, and the network generates spikes instead of just transmitting between layers that the weights. So when the spikes are very energy efficient because that's what they believe that how human brain works, because your brain doesn't consume that much of energy when you tries to learn or looking at some images compared to the current machine learning that is consuming a tremendous amount of energy to train on GPUs. So this is a very interesting network that we have looked at, and also in continuation from the previous work we have discussed, that we have actually merged the previous the NCP neurons, the model with spiking neural network, and you can actually see from the chart. So instead of we have used the same processing of the ECG, and you can actually see the GIF. You can see the spikes, and those are actually when we made this ECG data neuromorphic, so make it spike, make it event based, and then we have input this network or this data to spiking conv-LSTM layer, and before it fit into the neural network, the same NCP network that we have used in our previous study. And the key takeaway from the study that we have found is that there is a claim that when you use spiking neural network, there's usually a big drop in performance. But in this work, where we combine the spiking neural network and the NCP network, we actually did not observe a huge drop in performance. Instead, actually the performance holds up quite closely to the original model, and because it's now neuromorphic, or is using spiking neural network, it's actually saving a lot of energy, as we have presented here. So it's actually almost 100 times less energy usage compared to the traditional neural network that we have tested on. And also to actually.
Sorry, Jim. I think there were some questions about the spiking,
Okay.
neuromorphic approach actually. So because this is a super interesting topic itself, right? So I think the question is, can you elaborate on the biomimetic approach, which I think is referring to the neuromorphic or spiking, event-based types of models you're using. Are there other models based on this kind of approach, and is it specifically interesting for tiny systems and resource-constrained devices, which I think it definitely is. So maybe if you want to just elaborate more on the kind of inspirations for these approaches.
So I'm just actually reading. Is that the second question? Can you elaborate?
Yes, exactly. This is a question from Arthur on the biomimetic approach. Yeah.
In general, are there other models based on this kind of approach? Is it kind of... Oh, okay. So actually, there has been a growing attention in this field because of the energy problem that I have discussed earlier. So there have been so what I have been focused on is on the network, which is the software of the neuromorphic, and there has been a growing interest in actually designing neuromorphic chips. There has been some commercial product actually released, and but at the moment, I think neuromorphic chips and neuromorphic models are still at the earlier stage. So there's still a lot of research and developments going on in this field. And I have seen there are new type of neuromorphic chips that has been released in the recent years. And there are some new ways actually to train the neuromorphic models as well, has been released in the past 1 or 2 years. So it's still early, this model, but there has been a growing attention and application of this kind of models in at least in medical domain. Yes.
Nice. Well, thanks for that insight. Definitely beyond even the biomedical engineering, that topic neuromorphic has been interesting in tinyML for some time and across a lot of domains. So definitely huge.
Okay. I think I addressed all the questions. So yeah, I haven't finished on that work. So this is just the finishing up slide for that. So we actually try to deploy this model on microprocessor, and to see if on-device fine-tuning can happen. Because at the moment for neuromorphic models or for spiking neural networks, it's harder to train on a normal GPU or CPU. But just to demonstrate our proof of concept, we actually deploy this model on a microprocessor and use it to actually train or fine tune on the edge to actually see if this can be done. And we have also tested this model on how it handles with missing channels. This is because when you are, as I mentioned, for ECG data, there are 12 leads, and sometimes there might be 1 or 2 leads that is not in good contact with with your body, and the signals gets rough or it's just missing. So we are always it's just like a habit that we have, that we always test these models on missing channels to actually see how these models behave when there's a missing data, and is there a huge impact on the predictions of the model. And compared to the non-spiking version of the model, the spiking ones is actually handles the missing channels better. This may be because the neuromorphic models works on event-based data instead of the full data. So it naturally handles some of the missing data better than the traditional models. And we have tested on one single lead ECG data to see if that can be done with just one lead ECG, and to see if this model can be applicable for tiny devices, because usually for tiny devices you don't collect 12 lead ECGs, you just collect just 1 lead. Yeah, I think that's all for this work. So I think there's more questions. Should I take that?
Yeah. So the question that you could address here is, how do you envision the on-device supervised training of a model to work in a real-life application? And where is the labeled data coming from in medical applications?
Yeah, I think the labeling will need to be done. So we haven't figured out that part yet. So how you actually do the labeling, because you actually need a doctor or the practitioner to actually label the data. But for some applications, the patient might be able to label the data themselves and use that to actually train on device. And this is a very tricky area where there has been some works in fine tuning that you send the data outside the device for training or for fine tuning, and then you redeploy the models. But there's a growing concern about privacy issues in that approach, because if you send the data outside, you know, the data, you know, it's very easy for anyone with a bad intention to actually hack into the data, to hack into the server to
Right.
get your personal data. So there has been a lot of work in this area as well recently, to actually address this issue.
Got it. And I think there are a few people who are definitely interested to collaborate with you and Steve. So if, I don't know if you have it at the end of your presentation, but your email contact or however to get in touch with you, definitely a few people interested here. So we'll save that for when you want to share it.
Okay. All right.
Awesome.
So I'll keep going with the other part of the. So I think there's one more work that I would like to just briefly present. So this is just another study that we have done. So we have actually introduced the application of the S4D model and the NCP model that we have tested on. So we had just had a very interesting idea on both models have shown you know, compactness or like high efficiencies in model size, in parameters, when dealing with this kind of you know, at least in biosignal data. So we had an interesting idea on, you know, what if we combine the two models. So we actually tested, you know, this model. We actually merged these two models. We only used one layer of S4D layer, and then we have merged it with NCP model or NCP network with just 20 neurons. And we actually tested on raw ECG data, means without any pre-processing, and we actually achieved you know, a model that's so small. It's just like 242 kilobytes in terms of architecture, in terms of the model size. And also we have also as we are moving towards, you know, trying to see if this personalization can be happen on device, we have also tested this model to actually for, you know, on device fine tuning to actually see if that can be happen, if that this model is trainable on a small, relatively small edge devices. And I think it was possible. And also we have actually tried to find the limitation of this model. And how we did it is that you know, we actually try to push the limit of the model by further reducing the neurons and the architecture within the S4D layers, and we actually have achieved a model that is just 25 kilobytes, and it's still holding up the performance quite well. And also we have also tried to test, you know, if instead of using a long ECG data, we just use a very short ECG data, is the model able to make a very accurate predictions? And we actually have tried, you know, just using 2.5, I think it was 2.5 seconds of ECG data, and the performance was still holding up nicely. So this model was, so we think this model is quite interesting because, you know, not only it tackles the problem of, you know, reducing the number of parameters, and also it reduces the problem of latency, because if you are only using 2 seconds of data, the latency for on-device inference will be much shorter. So I think that's the summary of this work. So if you have any question, happy to address that now.
Ben, we'll give it just a minute or so for anyone who has some last minute questions here before we wrap up. But you know, thank you very much for the detailed and dynamic presentation. I guess quickly to wrap up with some final thoughts. What's next for your research direction? What are you and Steve working on next in alignment with this work?
Oh, okay. So actually I have actually just one slide on, you know,
nice.
just future work. So so I think after actually we have tested on several you know, promising networks that is small and efficient, we are still trying to actually improve the performance of the model. and and we are also very interested in. I think one of the questions earlier was regarding how on-device fine-tuning can actually happen. That is kind of the area that we are also interested in at the moment.
Nice.
So we actually, and I have mentioned to you, there's a conflict, there's a balance that we need to address where sending anything outside the device and keep everything on the edge because of the privacy issues.
Right.
So we are
Right.
also trying to address that with some new methodologies that we have recently have done some work. So I think there's some incoming. I think in the incoming days we might be releasing that work. It's kind of interesting because it's kind of a new methodology that we have proposed to actually maybe address this issue. Yeah.
Awesome. Well, that's super cool. I think we have a bunch of questions here, so we'll get through them in order here. So first question is, how can a person with a heart murmur volunteer to obtain this device and wear it and send you lifetime data during rest and during sports activity?
To obtain the device and wear it and send it to rest of. I'm not quite sure about this because for what we have done so far is we use usually use data sets that is either public or we have an agreement with. So we actually we did not even it's if it's a personal data, we actually get it from through the agreements that we have with hospitals or any other corporations. So we haven't really tested on how applying that on real person and try to do that.
Got it. Okay. Then next question here is, for a single lead ECG, where did you physically attach the sensor to the scalp?
I think there is certain devices that actually has been released in the market that is just this big, and I think it just attached there to actually collect just one lead ECG. So I think you can actually design a device and to train the model with the type of data you're going to connect with just one lead ECG, and to actually see if the model actually makes the good predictions.
Okay. And then another question, we talked about this a bit, but I think the question relates to, are you trying to take learning or fine-tuning on device?
For some of the work, we have tried that. And I think that's one of the directions that we actually have. So we think that keeping the fine-tuning process on device is beneficial comparing to sending it out to device in general.
Okay, nice. So we do have a couple of minutes here, so we'll go through these 3 questions we have. So have you explored federated learning using your models?
I have not used the federated learning for the models that I have, but I can see where this the question is coming from, because instead of sending your data outside, you can share the gradients and actually to actually fine tune the models. But there's one, I'm not sure if you are aware, there's a couple of papers that has been released in 1 or 2 years. There's growing concern with federated learning because there has been study done that to show that you can actually replicate the training data with the gradient that you shared outside the device. So that's quite and with just 20 lines of code, if I'm not wrong.
Yeah, that's a good incentive to use federated learning as one way to update models and achieve the learning and the on-device learning. So and that kind of relates to this other question, which we talked about again, I think a bit, Jim, but it's, how do you address model drift?
How do I address model drift? So that part of the question we haven't really thought on, but we believe on-device training can solve some of the drifting problems. Okay.
And I know it's late for you here, so maybe last question before we give you a break and we conclude here. So also, are you trying to do non-invasive EEG collecting devices?
Yes, I think in the group that the research group we have, I think a part of us is actually working on non-invasive and invasive EEG connection, devices. And yeah, so we have done a bit of work in that as well.
Fantastic. Fantastic. Well, on that note, I think we also have our forums as well we can use to keep the conversation going. Jim, Steve, I'd love to thank you on behalf of tinyML. If you can share your email address or get involved through the chat, however you like, that'd be fantastic. I think there are a few people interested to collaborate with you guys. So on that note, I think it'd be great to thank both of you again for your time, for making this happen today. And thank you to our attendees for being here on our live stream and on Zoom. Thank you again to our sponsors, to our executive strategic partners at tinyML. Thank you to our platinum strategic partners as well, Embed UR, to Sony AI Trails Deploy Vision AI at Scale, the gold strategic partners, ARM, Build the Future of tinyML, Edge Impulse, the leading edge building platform for EdgeML, Infineon, driving decarbonization and digitalization together, Neuromorphic Intelligence for the Sensor Edge from Inatera, Renesas, ST provides extensive solutions to make tiny machine learning easy, Synaptics engineering exceptional experiences, and also the silver strategic partners listed here. So thank you everyone for joining us. That concludes today's tinyML talk. We'll see you next week. Thank you very much.